No, I think we have to start from this one because I have to go to another place to bring it. Yeah, just 1 minute.
Okay, I can here is Shiladitya. I can share the screen.
Yes, please, Sheila. Alekha, can you hear us?
Hello?
Yes.
Can you
Yes.
wait?
So Shiladitya is sharing the screen. So if you
Okay, okay. So
can,
I'll
yeah, ask.
okay, okay. I'll
Yeah,
do that
and
because some setting I have to do. So I
no,
don't
yes.
know.
So
Okay.
it's normal. But
So shall I start now?
no,
yes.
wait.
So
Everybody can see my screen.
yes,
Yeah, I
yes,
can see. I can see.
yeah.
Okay, and slide.
So
No, wait, wait, wait.
today's
Yeah, slide is changing. Okay. So how it will we will like when so whenever you will say to change the slide, I will change.
Okay.
So we have the second speaker, Alekha Nayak, and he will be talking about bounds on sterile neutrino lifetime and mixing angle with active neutrinos by global 21 centimeter signal.
Thank you, Dr. Anish, for giving me the opportunity to present my work in the seminar series. So today I'll talk about bound on sterile neutrino lifetime and mixing angle with active neutrino by global 21 centimeter signal. So please change the slide. So my plan of the talk, first I'll introduce what is the 29 centimeters global signal, and then I'll talk about using this global 21 centimeter global signal, how to constant the sterile neutrino decay width, and from there on we'll discuss how we can constant the mixing angle and between the sterile neutrino and the active neutrino. Then I'll conclude it. Then change. So first we'll discuss about what is the 21 centimeter line. The 21 centimeter signal arises from the hyperfine interaction between in the ground state hydrogen atom due to the interaction between the magnetic moment of electron and proton. So what happens here? It is after the, please change the slide. Can you change the slide? Please change the slide. Can you hear me? So what you can say, this is the spin flip interaction between the in the hydrogen at ground state hydrogen atom. In the ground state hydrogen atom, you have proton, you have electron, and when the two spin are parallel, this is the like the triplet state, and when the two spin are anti-parallel, that is the singlet state. When there is a transition happens between the triplet state to singlet state, the wavelength of the photon that will emit is the 21 centimeter. So using this 21 centimeter, how we can study the cosmic dawn era and the dark ages, we'll discuss in this talk. Please change the slide. Okay. So the motivation, like for the to study the 20 centimeter signal, is it will give you the information about when the universe first star is born, and like first structure is formed, and it also hints about how the baryon interact with the dark matter. Also, it can give the hints about, and you can constrain the dark matter properties using the 20 centimeter signal. So what happens? I will first talk little bit about how this 21 centimeter signal, where we expected to see this one. So we know that universe start with a big bang. At that time, everything was in the plasma state. As the universe like cools down, what will happen? The neutron and proton, they combine to form the neutral hydrogen atom. And when all the all the electron and proton, they combine to form the from the hydrogen atom, that is the end of the recombination. And after this time, when the since now hydrogen is a neutral atom, now photon cannot interact with it, so it will travel. Uh, so that is the CMB. So this photon is observed today as the CMB photon. So after this recombination here, it followed by a dark ages, because at that time the photon cannot interact with the gas, and after that this is called the dark ages. So after this dark ages, there will be followed by a cosmic dawn era, when after that what will happen, the first star will form here, and after the star formation, it will start to emit X-ray, Lyman alpha photon, and it will heat the gas and it becomes ionized. So this 21 centimeter signal will be gone. So what will happen after the end of the recombination, the universe is totally filled with the neutral hydrogen atom, and it will and there will be photon, and which they are not interacting. To know the what happens in this era after the recombination up to the reionization, we need to study this 20 centimeter signal. Please change the slide. Okay, so the transition from I, as I already told you, the transition from the triplet state to singlet state is forbidden. Like it's the transition rate is 3 into 10 to the minus 15 second. But as I already mentioned, that universe was totally filled with hydrogen atoms. So the transition probability into the number density will give you, like, we'll get a sufficient number of transition to observe today. Please change the slide. Okay, so before we going to discuss about what we are going to observe, first let's discuss about something called, some terminology called the spin temperature. This spin temperature, it is the relative number density between the triplet state, that is the when the spin are parallel, to the singlet state when the spin are anti-parallel, is given by N1 by N0, which is equal to G1 by G0 exponential minus E21 by Ts. This Ts is the spin temperature, and E21, this is the energy correspond to the 21 centimeter wavelength photon. So which is equal to 5.9 10 power minus 6 electron volt, and that correspond to that temperature is 0.068 Kelvin. And G1 by G0 equal to 3. And as you can see that if temperature Ts is high, that is the spin temperature is high, there will be more number of hydrogen in the triplet state compared to the singlet state. So everything, like the whether we are going to see a absorption signal or a emission signal, everything will depend upon this spin temperature. Please change the slide. Okay. So what happens, that photon we are expecting from the radio photon, right? So the 20 centimeter wavelength correspond to a radio photon. So in the Planck distribution, if you go to the radio range, so this can be approximated. The intensity can be approximated. I nu can be approximated by 2 kb TB nu square by c square, and here this TB is called the brightness temperature. So at low frequency, we can approximate the intensity by this one, and this intensity is proportional to your temperature. And what we are going to observe, not the brightness temperature, what you observe in the antenna is not the brightness temperature, actually it is the differential brightness temperature, which I'm going to talk in the next slide. Please change it. Okay, so this is the differential brightness temperature which we write as T21. So that is TB minus TCMB, and which you can say equal to 1 over 1 plus Z T spin temperature minus the CMB temperature. So you can see that T21 is proportional to TS, the difference between the spin temperature and CMB temperature. Then there is 1 minus exponential minus the tau, that is the skin depth. So that is the optical depth. So the T21, it can be positive, it can be negative, depending upon or it can be 0. If T21 is equal to 0, then we don't observe any 21 centimeter absorption signal or emission signal. So what happens, this is, if you pictorial you can see, this is the CMB photon that will be there after the end of recombination. It will pass through the hydrogen atom which are there after the recombination, and what after passing through this, what we are going to observe, that is TB. So the difference between this TB and TCMB, that we observe in the antenna. So depending upon, from here you can see this T21, it is 0 when the spin temperature equal to CMB temperature, and it will be greater than 0. That means if T21 will be greater than 0, that means spin temperature is greater than the spin temperature, which is somehow related to the gas temperature. That gas means the IGM, intergalactic medium, that temperature. If that is greater than the CMB temperature, then T21 will be greater than 0. We'll see a emission signal. And if CMB temperature is less than the gas temperature, that means your photon, that temperature is less than the gas which through it is passing through, then it will absorb by that one. So then we'll expect a absorption signal. So can you change the slide? Okay, so that is what I have written here, like the detectability of T21 depend upon the spin temperature, and if TS, that spin temperature, is greater than the CMB temperature, we observe a 21 centimeter emission signal. If spin temperature is less than CMB temperature, we observe and 21 centimeter absorption signal. If TS equal to TCMB, there will be no signal. So the whole thing, like whether we are going to see a absorption signal or emission signal or no signal, that whole thing will be depend upon the spin temperature, which is given by this relation Ts inverse, which is equal to Tcmb inverse plus x alpha T alpha inverse plus xc Tk inverse divided by 1 plus x alpha plus xc, where this x alpha is the okay, so x alpha is the coupling coefficient due to the Lyman alpha scattering, and xc is the this is the coupling coefficient due to the atomic collision, and we know that CMB temperature is equal to 2.72 Kelvin plus 1 plus Z, where Z is the redshift. So next we'll discuss how the evolution, like we are going to discuss what is the evolution of this 210 centimeter signal during the dark ages and the cosmic dawn era. Okay, can you change slide? Okay, so before we discuss that, first discuss about what is this collisional coupling coefficient xc, which is given by xc. So after the recombination, we have hydrogen will be there. There will be some amount of residual electron which didn't get recombined, and there will be some residual proton will be there. So the collisional coupling, that will be the combination of collision between hydrogen electron, and hydrogen proton. And in general, the hydrogen coupling coefficient dominant, it will give you the dominant contribution among the three contribution I've written here. Okay, please change the slide. Okay, so then there is something called the Lyman alpha, that Lyman X alpha that we have discussed, Lyman alpha coupling, which is X alpha 4, which is given by 4 P alpha divided by this expression is given here. So when this Lyman alpha coupling will be important. So in the very beginning, after the end of the recombination, this X alpha is equal to 0. So this will be important when at around redshift around 20, the first star will be born. After that, there will be Lyman alpha that will be emitting from the stars. So after that only this X alpha will be important. Now what will happen when the first star will be born? then there will be Lyman alpha radiation will be there. So because of this one, there will be atomic transition will happen from n equal to 1, that is the ground state of the hydrogen, to n equal to 2, the fast excited state of the hydrogen. This is something called there will be some indirect spin flip will happen. This is something goes by the name Orthosian field effect. So the selection rule is given here. So next I will discuss about the evolution of the 21 centimeter signal in the dark ages and the cosmic dawn era. Please change the slide. Okay. So first, the recombination ends at redshift equal to 1100, close to this one. So after this one, what will happen? There will be some residual free electron will be there, some residual free proton will be there, and this residual electron, and there will be hydrogen gas will be there. So what will happen? There will be Thomson scattering will happen. Because of this Thomson scattering, the CMB temperature will be equal to the kinetic temperature of the gas because of the coupling. And because of this one, what will happen? The CMB temperature become equal to the spin temperature. And if I go by the equation for the TS inverse, since there will be no star formation happen at that time, X alpha will be 0, and XC, that collisional coupling between the hydrogen electron, hydrogen proton, which is much greater than 1. So that equation becomes TS inverse equal to TCMB inverse plus XC TK inverse divided by 1 plus XC. So because of the Thomson scattering, the CMB temperature, they are in equilibrium. The CMB temperature and the kinetic temperature will be remain same. So I can take the CMB from in the numerator, I can write TK equal to TCMB. So this 1 plus XC I can take common. So the spin temperature becomes CMB temperature. So if the spin temperature becomes equal to the CMB temperature, there will be no signal during this period. So that is this will happen till this process, this Thomson scattering, which maintain the equilibrium between the gas and the CMB, this will happen till the redshift equal to 200. Okay, the next slide. So after this, this 2000 redshift, what will happen? The gas will that will cool adiabatically like 1 plus Z square, and the CMB temperature goes as 1 plus Z. And what will happen in this time, that kinetic temperature of the gas will fall below the CMB temperature, but the collision between the gas particle, that will drive the kinetic temperature to the spin temperature. Still there will be no star formation. That's why the X alpha will be equal to 0, and the collisional coupling is still greater than 1. So we can write TS inverse equal to TCMB inverse plus 1 plus XC plus TK inverse. Since XC is much greater than 1, we can, in the right hand side, we can neglect this the first term. So what will happen? This will be equal to TS equal to TK. The kinetic temperature of the gas will be equal to the spin temperature of the gas, but because of the adiabatically cooling of the gas, the temperature of the gas falls below the temperature of the CMB. And when this happens, so that means TS, the spin temperature, is less than the CMB temperature. When this happens, an early 21 centimeter absorption signal is expected that time. So between these two redshifts, because the T21, that differential brightness temperature will be less than 0, so we expect a early absorption signal during the dark ages, that is just after the recombination, like after redshift equal to 200 till redshift equal to 40. So please go to the next slide. So after redshift equal to 40, what will happen? The universe has expanded a large amount of so what will happen? The gas density that will fall down, because now in a particular volume there will be very less amount of gas will be there. So what will happen? The gas density will fall down, and the collisional coupling becomes very less, and still there is no star formation. Here I have written that lower limit to be Z star, because we don't know the exact time when the first star will form. So since there is no star is formed, so the Lyman alpha coupling is still 0, and because of the expansion of the universe, the gas density has decreased, so the collisional coupling is much less than 1. So this spin temperature Ts inverse, which will be equal to TCMB inverse plus 1 plus Xc plus Xc Tk inverse. So what will happen here, since Xc is much less than 1, you can come in the first term, in the denominator of the first term, so you can 1 plus Xc becomes like 1. So what will happen? And this Xc is much less than 1, so you can neglect the second term. So this will be equal to Ts equal to TCMB. So we already, I have already discussed that when T spin temperature equal to the CMB temperature, the differential brightness temperature will be, that is T21 will be equal to 0, because that depends, the differential brightness temperature T21 is the difference between the spin temperature and the CMB temperature. So when Ts equal to 2 CMB, spin temperature Ts equal to TCMB, there will be no 29 centimeter signal we expect in this period.
Okay, I have a question.
Please go.
So
Next slide, please.
temperature, the density of the gas has been decreased due to expansion. I agree, but in smaller structures like dark matter halos or something, there maybe density of gases might be high.
Okay. So in general, what we are going to, like there is no, that time there will be no structure out there, right?
No, I mean, when fast star formation has started, that means dark matter halo has been formed, right?
No, this is not the period. I have since I have already mentioned, na, there is no star has formed at this time, because X alpha is still 0 here.
Yeah, but when already clump of glass cloud has started to form.
Yeah, the clumping has started, but but this time still the means what will happen when the universe, okay, that I think this time the gas density as a whole, if you say look at statistically, it is still like, if you at some point, like in the galactic dark matter halo, the density may be higher, but if you look overall, if you take the average, I think that will be still less than that. This will be less.
Oh, okay. Oh, okay. Thank you.
Collisional coupling will be still less than 1.
Okay. Thank you.
So please change the slide. Okay. So this is the in this phase, what will happen, the in between the that we know at what time that halo has formed, like when at what time the fast star is formed. So that's why this is that is still unknown. We expect that this will be around 20 redshift around 20, the fast star will be formed. So after that there will be Lyman alpha photon, and because of this Lyman alpha photon, the Uthusen field drives the spin temperature to the kinetic temperature, that is Ts equal to Tk, because that indirect spin flip. And still here, since because of the adiabatic cooling, the kinetic temperature of the gas is still below the CMB temperature. So here in the first time, the X alpha is not 0, which is much greater than 1 because of the fast star formation. And because of this Lyman alpha coupling, the Lyman alpha photon scattering, the temperature of the Lyman alpha will brings that kinetic temperature of the gas, which will be equal to T alpha. And if you put that everything into that equation, Ts inverse, which will be equal to TCMB inverse plus 1 plus Xc plus 1 plus X alpha plus Tk inverse. And here the first, if you look at the right hand side of this one, the Xc is less than 1, we can neglect that one. X alpha is much greater than 1, so we can neglect this, the first term. So what will happen? Ts inverse will be equal to Tk inverse, so that is Ts equal to Tk. But because of the adiabatic cooling, the Tk is less than Tc, temperature of the gas is less than TCMB. So here that means Ts is less than TCMB. So we observe this period is called the cosmic dawn era. So in this period we expect a 29 centimeter absorption signal. Okay. So please go to the next slide. So after this one, what will happen? After when there will be large amount of stars will be formed, and there will be X-ray from the active galactic nuclei that will hit the IgM, and because of the heating, the intergalactic medium, the temperature of the gas will be more than the temperature of the CMB. So, and because of this Uthusson field effect, T alpha equal to Tk. So, in this case, since temperature of the gas is much more greater than the CMB temperature, we expect a emission signal. Finally, so I should have written another, that reionization will happen around say redshift equal to 5 or 6. So after that, what will happen? All the neutral hydrogen becomes ionized. So when there will be no neutral hydrogen, we don't expect any signal. Please send the next slide. Okay, so this is the pictorial. You can see there will be after the end of recombination, there will be no. This is the in the y-axis, the brightness temperature is given in millikelvin. In the below in the top, redshift is given. So you can see up to redshift equal to 200, there will be no signal, and after this 200, because of this, I already explained, the first signal will appear between 200 to 40. So you will expect that that absorption signal here, and this is all in negative, right? So T21 is negative. So then there will be no signal. Then there is this signal is there in the redshift around 2017 here. This is the cosmic dawn era. You see a bigger signal here, and then after that there will be emission signal. Then when the reionization happen, so hydrogen will be reionized, there will be no signal here. So in the standard lambda CDM model, in the standard astrophysics, the differential brightness temperature at Z equal to 17, that is the standard expected value is minus 220 millikelvin. Here it should be greater than minus 220 millikelvin. That correspond to the gas temperature is equal to 6.8 Kelvin at redshift equal to 7. This is actually important. We have to remember this number. So this at Z equal to 7 in the standard lambda CDM model, we expect the gas temperature, which is mostly the hydrogen atom, or some part of helium will be there. So it will be more, you expect that temperature, gas temperature, to be 6.8 Kelvin. So please go to the next slide. Okay. So in 2018, Baumann, this is a Nature paper, they observed in the edges
Hello?
experiment, they observed the brightness temperature with 99% confidence
Hello?
interval. Yes.
We have 10 minutes left.
Okay. I started a little late, right? So what they expect that they observed that the signal to be, which was to be supposed to be minus 220 millikelvin, they observed that will be minus 500 millikelvin. That means the what happens? That means that this corresponds to the gas temperature 3.26 Kelvin. So in the standard astrophysical model, that says it should be 6.8 Kelvin. So what we got from this edge signal, that this should be the gas should be much colder, like what we expect from the standard astrophysics. So how you can explain this signal? Like either to T21 generally depends upon Ts minus TCMB. Either you cool the gas. How you can cool the gas? You can interact, if the baryon, like the gas interact with the dark matter. Dark matter is much colder than the baryon. It will interact with the dark matter will interact with the baryon. Then baryon temperature will cool down. This is one of the proposal. Or else you can produce radio photon, which can explain this the T20 and the brightness temperature, differential brightness temperature to be minus 500 millikelvin. So then there is another possibility. So what we can say, this is not about the edge signal. Suppose we know there is dark matter there. If the dark matter that can annihilate or it can decay, so what will happen? Because of the annihilation and decay, it will inject energy into the intergalactic medium, and that will raise the gas temperature. If it raises the gas temperature, then we instead of getting a absorption signal, it can erase out. If the dark matter annihilation decay, that strength is so high, then it can erase out. Based on that, we can put constraint on the dark matter decay width, as well as the annihilation rate. In this talk, I will talk about the sterile neutrino, which is a dark matter candidate, how we can put constant on the sterile neutrino parameter space. Can you go to the next
Okay,
slide?
I have a question. So what is H1,
Yes.
H2, H3?
Hello?
What is H1, H2, H3, H4?
These are like, this is the black one is the central, like this is the median of all this observation. from this.
H2.
H2, yes.
Okay. So and other
That
two?
is the best speed value. And that
Different
corresponds to
observation?
-5. Yeah, this is just observation.
Okay, so different observations or for same observation for different.
From the same observation.
Okay, thank you.
Can you go to next? So here, what I'll discuss how like we know that sterile neutrino, this is a dark matter candidate, so it can decay to, there are several modes of decay, but it decays to sterile neutrino, goes to active neutrino plus photon. What will happen? This photon will interact with the intergalactic medium and it will raise the temperature of the gas temperature, and we'll see that how much the decay should be, so it cannot miss. From there, we can constrain the parameter space of the sterile neutrino. Okay, so the what happened? Okay, so this is the evolution of gas temperature. Yeah, you go to the next slide. So this is the standard lambda CDM model gas evolution equation. So first term, this is the T gas dT by dz. So the first term on the right hand side, that represents the Hubble expansion. Then this is the this is the Compton scattering, and this this is the electron fraction evolution equation looks like this one. This is a coupled differential equation. If you solve with the initial condition, like at T gas equal to TCM at the end of the rate combination equal to 2.72 Kelvin 1 plus Z, Z equal to 1100, then we can get the T gas at redshift 17 equal to 6.8 Kelvin. This is the standard thing. Okay, so please go to the next one. So gas evolution in the presence of sterile neutrino decay. What happens because of the decay of the sterile neutrino? It can inject energy. So you can say the first term in the gas evolution equation, the first term is the Hubble expansion, that is the cooling. So the last term is the heating term. This comes with a negative sign, and here this epsilon, in this epsilon this epsilon contains the lifetime of the sterile neutrino as well as the mass of the sterile neutrino. That we'll discuss in the next slide. And because of the sterile neutrino decay, the electron fraction evolution equation change like this one, where E alpha equal to 3 by 4 epsilon naught. Okay, please go to the next slide. Okay, this epsilon, which was there in the first gas evolution equation, that is called the energy deposition rate. Like when the sterile neutrino decay, how much energy will be deposited into the gas, that will given by this expression, where Fs, that is the fraction of sterile neutrino that are decaying. Here we take whole of the, like what we assume that the whole of the dark matter will be formed by this sterile neutrino, that Fs equal to 1, and then this is rho nu s, which is the, we can say this is equal to mass of the sterile neutrino times the number density of the sterile neutrino, and here we can take this to be the number density of the dark matter at present. Okay, then we have the this is the lifetime of the sterile neutrino, and FABS, that is the energy deposition efficiency into the IgM by the decaying sterile neutrino. And yes,
Hello.
yes,
We have 2 minutes left.
yeah, please. Okay, so by using
have-
all this equation, okay,
Oh, I have
so
a
we can
question.
get,
So if x equal
yeah,
to 1 means a fraction of sterile neutrinos that are decaying. So that means
yes.
whole of the sterile neutrino decays.
No, that means we are taking not the whole, that means how much we are taking, like the how much fraction like of the dark matter will be the sterile neutrino. So here we are taking whole the fraction, like the total dark matter is composed of the sterile neutrino.
Okay.
Okay. So please go to the next slide. Okay, you can see here what happens if I increase. This is the black you can see here, this is the CMB, this one is the CMB temperature, how the evolution of the CMB temperature, and this solid line, this black line represents when there is, this is the standard lambda CDM model. So when you have, there is no heating is there because of the decay of the sterile neutrino. When you include the decay, the temperature is going to rise, and this shaded region, this correspond to the redshift around 17. Okay, that in the x-axis we have the redshift 17, and because of this one you can see when we increase the mass, okay, when we decrease the mass, the heating effect is more, because what happens, the density is equal to mass times the number density. If mass is high at a particular redshift, the number density is less. That means less number of sterile neutrons are decaying. So that means the heating will be less. So please go to the next one. So similarly here, for a fixed mass value, if you have large, if the lifetime is larger, what will happen? The decay rate, if the lifetime is larger, then the gas heating will be less. If the lifetime is smaller, the gas heating will be more. That is represented by the blue line represents the 2 into 10 power 26 second. That is the smaller one. Then this one represents the larger lifetime. So you can see the heating will be more here. Okay, so using this one, okay, so because we okay, go to the next one. Using this one, what do we expect, that the T21 in the standard lambda CDM model is minus 220 Kelvin. What we expect, that let's say it will be minus 150 Kelvin and T21 is minus 100 millikelvin. Then what is the parameter space we have scanned for at redshift equal to 17? This dotted line, this dashed line are for these two, and this dotted line, this includes another heating effect that I have not explained here. So using this, like at Z equal to 17, we say that the differential brightness temperature is minus 150 millikelvin. Then what is the parameter space? That is we have scanned here. Once we scan this parameter space, then we can get the relation between the mixing angle and the mass that I have shown in the next slide. Okay, this is that one, the relation between the mixing angle between the sterile neutrino and active neutrino with the mass, and this region is excluded by the X-ray constant, and whatever you can say in this range you have a stronger constant out here. Here there is a more stringent constant coming from the 21 centimeter line. Okay, so finally I conclude this one. Okay. The lifetime that we have already discussed, the lifetime of the sterile neutrino decreases when one increases the mass of the sterile neutrino, because the number density, once we increase the mass of the sterile neutrino, number density decreases. If the number density decreases, that means less number of the neutrino are decaying to the active neutron and photon. So since there is less number of photon are there, so the heating effect will be less. Similarly, we have shown that to increase the gas temperature, we have to decrease the lifetime of the sterile neutrino, and this is the upper bound on the mixing angle for mass range 2 kV to 50 kV. We got